So yeah, we at nFrames, we are mainly focusing on kind of this large-scale city mapping application, as Bernd has put it already quite nicely. So what you can see here is the city of San Francisco, for example, which was created with Shure. So what we focus on is kind of an automated workflow of generating 3D models, or in general actually 3D content. And I will talk a bit more about what kind of 3D content that is and what you can do with it. And let me actually just start by jumping right in into my presentation. So I'm Toby from nFrames. I will talk a bit about this large-scale city reconstruction from imagery and LiDAR. And I myself have the background of actually starting at the HDM and also was directly working with Bernd on my master thesis in visual effects, and then moved over to London to MPC, where I worked on some feature film visual effects. And now I'm back in Stuttgart for 3 years now, working for nFrames. So for me personally, it's also kind of a nice kind of round trip to come back to visual effects or give this presentation today. And I would actually like to start with this image. Some of you might have already recognized where we are. This is Stuttgart. Down here in the middle somewhere is Gutbrot, where we are sitting today. And this is one of the data sets that I think was flown even this year of the city of Stuttgart. So let me start a bit by talking about who we are at nFrames, what kind of technology we work with, and what kind of workflows we offer. And I would actually start with, I think, one of the most important parts, in my opinion, and this is kind of where we come from. So we've been founded 5 years ago. Back then when I joined, I think which was like 3 years ago, we were around 9 people. Right now we're a bit more than 20. And we're just sitting here in Stuttgart West, so I actually just walked here from the office just now. And what we do is we see ourselves kind of at the edge between research and actual large-scale mapping applications. So kind of transferring this knowledge from research into real world. And what we do is really focused a lot around customer success. So we're a very customer-driven company, I would say. So this is our team. This was last year on a nice hike. This was on a retreat. This is something that we do twice a year. And this is just our office, our regular working environment, us at the B2 Run, and us at Intergeo, which is one of the important trade shows for us. Actually, this year it was in Stuttgart. So yeah, moving on to what we do. I actually put in the slide because I think it sums it up quite nicely. We are a photogrammetry and LiDAR software company. So we do develop software, and we are trying to empower professional mapping. So this is really what we focus on, is this professional grade mapping. And how does this look like in everyday life? So our customers typically, they fly with mostly manned aircrafts over cities, for example, and they collect either LiDAR data or photogrammetry, or actually image data, images with overlaps. And from these images, we create point clouds. So going into that, how this actually looks like is our input, as I said already, is either imagery or LiDAR data. And on top of that, one of the things that might come as a bit of a surprise is that we also require orientation data. And the reason for that is actually that this is quite common, I would say, in our industry. So a lot of people do supply orientation data already along with their imagery. And what we do from that is we produce all these nice outputs. So 3D point clouds, textured meshes, what you saw just now, and also true orthophotos and digital surface models, which I will talk about in a minute. So yeah, in general, how does our pipeline work? I think most people have already seen it before. We essentially have images with overlap. We search for correspondences in these images. And out of that, we can actually triangulate a point cloud in the end. So how this looks like when it comes out. So this is the typical stereo matching application that you might think of if you have 2 images. But actually what we are really doing is multi-view stereo. So what you can see in the middle. Which means actually a lot of images see a certain position, and based on all of these images we triangulate 1 point for every pixel. And out of that, you can then, for example, derive these digital surface models, is what we call them. So essentially, we have one height value per XY position. And this is what you see here. So actually, you see that the facades and all of that is missing. And the reason that we do this is because we would like to derive height maps or digital surface models in that sense. So this is what you see here on the left. This is in the end an image containing per pixel one height value, so kind of color encoded here the height of every pixel. And if you take that and texture it, what comes out of it is a true ortho photo. So this is what I mentioned before. What the other kind of big product that we produce apart from 3D meshes are these true ortho photos. And I would just like to give you a bit of context because I'm sure some of you won't be familiar with what they are or why they are relevant. With this slide, so in the mapping industry, this is actually a very, very common product. I would say right now even more common than the 3D models still. So people traditionally create, or how they used to create ortho photos was essentially by stitching images. And if you imagine that you have images with parallaxes, what you end up is some sort of ortho photos with building lean. So what you can see right here is that this building actually leans into the street and also shadows a lot of other objects that would be there in reality. And with the process that I explained before, you can actually create kind of artificial, real orthographic images. And if you now imagine what somebody tried here, for example, was to create the building footprints, which would, for example, be relevant for cadasters. And as you can see, this is essentially impossible from the left. But that's how people used to work, actually. And nowadays, most of them do it with true ortho photos. And one example here is that all of the German municipalities, or the Bundesländer, do produce this in, I think, a 2-year cycle for all of Germany. And a lot of them do that with Shure, actually. So yeah, here just some more examples of how this can look like in the end if you have such a true ortho photo. So you can see there's no building parallax in any way. This is, for example, the city of Warsaw. Yeah, and here also just a list of our customers. As I said, the German Bundesländer are in there. There's also a lot more. I mean, a lot of our customers are also mapping companies that that actually do fly themselves. So they own aircrafts, they own million-dollar cameras to do this kind of acquisition. So we're really kind of focused there on the professional mapping market. And just to talk a bit about what the typical challenges in this industry are. I would say one of the big topics in this industry is really just scale. So as I said, people are trying to produce all of Germany or even more than that. And so, of course, they want to do that in a way that is kind of fast and at the same time scales up to arbitrary dataset sizes. They want to really create accurate outputs, so like measuring great outputs. You actually want to be able to measure in your results in the end. Yeah, cost is, of course, always a topic, and then also expertise. So traditionally, all these kind of photogrammetry softwares were very complicated, I would say. And nowadays, it's going more and more into the direction that you don't need in-house experts. You just want some software that you put your images in and you click go, and then the result comes out. So yeah, so this is actually the values that we're trying to tackle these kind of issues. So precision is something that's really important to us. So there we often talk about edges, I would say. So this is one of the reoccurring topics all the time, building edges. How accurate are they? How sharp are they? Performance, of course, usability of our software, the scalability, which is one of the topics that we tackle. I will tell you in a second how we do that. We, of course, offer integration and also modular workflows. So yeah, one of the things that we also focus on for the scalability aspect is the distributed processing topic. So essentially what we do is we try to split up projects into chunks, and you can either process them on one machine or on multiple machines, doesn't really matter. You can put it in the cloud if you want to. So in the end, what you end up with is just individual chunks that you process once at a time, so you can kind of scale up to arbitrary dataset sizes, and in the end we put it back together. Yeah, so now coming back to what I showed you right at the beginning, which was about 3D meshes, I believe. So I think this, for most of you, will be probably more interesting. So yeah, what we do is, of course, we don't only toss away the facade information, like I told you at the beginning. In other cases, we, of course, also want to keep it. So this is an example of a 3D point cloud of Frankfurt, where we applied our point cloud filtering algorithm. And then if you put that again into our next module, which would be the meshing module, out comes a 3D mesh. And here are some more examples. I've shown you before the city of Warsaw. Here it is again as a 3D model instead of a true orthophoto. Yeah, here also some geometry. And with texture, of course. Yeah, and this is actually another nice data set to show. One of the big topics, of course, also in our industry is not only manned aircrafts, but also drones are becoming increasingly more important, I would say. Drones are capable of carrying more weight these days, are capable of flying longer. So it becomes more and more interesting to use those also for acquisition of data sets. So yeah, there's multiple topics, and this is one actually quite nice data set where this was also done in a larger scale, I would say, on the city of Landshut here in this case. Yes, so at the beginning I've also talked about LiDAR, and this is one of the topics also quite dear to myself because I've been working on it quite a lot. So LiDAR stands for light detection and ranging. And it's essentially an active measurement system, so a laser scanning system. So you shoot an active laser beam and you kind of measure how far away a point is. So it's a distance measurement principle. And in general, it's quite interesting, especially in combination with photogrammetry, because it just has different properties than photogrammetry. So you usually have a lot lower point density, so you have less detail that you can resolve, but at the same time your measurements are much more accurate, usually, at least in depth direction. Photogrammetry, on the other side, you can almost create arbitrarily dense point clouds, and there the challenge is more or less to figure out again which points are the good ones in the end. So putting them together is quite interesting. Also, if you think about, for example, occlusions, which are an issue in multi-view stereo scenarios. If you have very narrow courtyards, for example, it's very hard to get multiple images of that courtyard, because as soon as you move a bit with your airplane, you don't see into the courtyard anymore. So you cannot really reconstruct anything there. And this is different for LiDAR, because there you just need one laser beam that hits the ground within the courtyard and you have a point. So yeah, here are some examples of our integration. So on the top you can see a geometry that we derived just from LiDAR data, and you can see it's pretty coarse. They have like 10 points per square meter in this data set, something like that. Whereas in the photogrammetry case, we have a point, in this case, every 4 centimeters, I believe. So yeah, putting it together, you can kind of see the benefits of both worlds in that sense. You get the noise reduction through LiDAR, and at the same time the detail through photogrammetry. And then on the right you see, of course, the textured mesh of San Francisco. And here are some more examples of this type of integrated processing. This is the city of Rotterdam that we processed. This is also with LiDAR and imagery, and this one is also quite special data set in that sense, I would say, because it's the overlap of the imagery is quite low. So this is one of the big topics that determines quality of the point cloud that comes out of photogrammetry, is how much image overlap do I have. And this is quite low in this case, but actually because we were able to add the LiDAR data in here, we were still able to retrieve really nice results. Yeah, and this here is the city of Eindhoven also. So yeah, actually one of the last topics that I want to talk about is also quite an interesting and quite a modern one, I would say. This is about deep learning. So one of the things that traditionally is a very, very big challenge is water, out of multiple reasons. Usually it moves at the same time, it reflects a lot of light. Sometimes you can see through it, sometimes you can't. So it's really hard in multiple images to figure out which points match. So finding correspondences is close to impossible, I would say. So one of the ways that we've been tackling this, or are currently tackling this, is with deep learning. So what you can see is, so it's kind of a teaser, it's not in our software yet. It's the results of a neural network that we've trained. And this is actually a nice use case for the city of Rotterdam again, because it has a lot of water. And you can kind of see the prediction on the right. So everything where you see white, the network is quite sure that it's looking at water. Everything where it's black, it's not looking at water. And we've actually gone through the process and have done the test ourselves, essentially. We've, on the right, manually created a shapefile with lots of labor. And on the left, you can see the manually extracted results, which is already pretty close and saves you a lot of time in that kind of process. Yes, so here again for the city of Stuttgart. And one of the big topics also why this slide is in is usually bridges. So this is something that really suffers usually from the artifacts that you have within water. People want to recreate their bridges in an accurate manner, and if you just have noise around it, it's really hard to distinguish where the bridge is. Yeah, and then here, finally the mesh where we use this water body. So essentially we've extracted from the shapes that I've showed you before. We were kind of able to extract in 3D the information where the water is, and we're able to flatten this area and texture it and kind of get perfectly looking results within the water area. So yeah, that already brings me to the end of my presentation. One of the important things that I also still want to mention is, of course, we're here in Stuttgart, and we're also actively looking for developers still, so feel free to contact us or talk to us just right now. Konrad is also with me here. So